Okay, 皆さん、こんにちは。Zamurai Engineer です。So, in this module, we will again go back to our discussion, resume the discussion on compression members. And one of the things that we always recall when we talk about compression members, we always look at columns, because columns is number one and constructive example of compression members. Okay. So let us therefore take a look, looking back on our discussion for columns. So we have technically we call that as we call that column as axially loaded compression members. So anyway, that is our chapter 5. So here is our chapter 5. Okay, let's see. Actually, loaded compression members. We already tackled several discussion out of this topic, but it's better to return, resume, and rewatch and retook this discussion, because it is very important. Okay, so after having your footings, your foundation, then we will have now ready to put up the column. And again, column is one very constructive example of compression members. So actually, column is an axially loaded compression member. So we have in this discussion, we have there are three general modes, okay, of failure when we are talking this. So again, just to remind you, we already discussed these things. We have what? Flexural buckling, local buckling, and torsional buckling. These modes of buckling are briefly defined. It is formally defined. Flexural buckling, it is also called Euler buckling. So last meeting, if you can recall, we talked about Euler buckling. We have the Euler formula. Okay, and it is the primary type of buckling discussed in this introductory chapter. So every introduction, we have Euler type of buckling. Members are subjected to flexure, bending, and when they become unstable. So that is the description of what we can say as flexural buckling. Okay. So, if you can imagine why column, is it possible that column could experience flexural buckling? Flexural meaning bending. Yes, still column is experiencing flexural bending or flexural stress. Okay? And you will see that there are several samples, there are several ways that it could fail, there are several loads that could be let us attribute the cause from those loadings. So there are limitless amount of application currently, okay, that would result in flexural buckling failure. And number two, local buckling. This occurs when some part of the cross-section of the column are so thin that they buckle locally in compression before other modes would fail. So this susceptibility of a column to local buckling is measured by the width thickness ratio. So width, okay? So meaning of the width, so there are two dimensions with regards to the cross-sectional area, and the smaller one is what we call the width. Okay? And width divided by thickness, that is our width thickness ratio, which is a not just a ratio but a variable that we would like to look into when we are going to study local buckling. Okay. And number three, flexural torsional buckling. Okay. This may occur in columns that have a certain cross-sectional configuration. So these columns fail by twisting, meaning torsion. So it could be by combination of torsion and flexure. Okay. So those are the things that we need to understand. We also discussed previously the slenderness ratio, okay, L over R. Okay. So that comes out from the formula derived to Euler force and Euler strength, Euler stress. Okay. So there is a slenderness ratio in Euler stress. Okay. So the Euler force, compressive force formula, we divide both sides by area, if you can still recall. Okay. And because there is a relationship between area and inertia and radius of gyration. So actually, what radius of gyration, let us review, is equal to square root of inertia divided by area. Okay, some important concepts here. Okay. Okay. A column is a more critical member in a structure than is a beam or tension member, because minor imperfections in materials and dimension mean a great deal. Okay, take note. Okay, although in computation, we have a very simplistic computation last meeting of how to design, how to analyze a column. a more complex design and analysis is there for beam, but still column is a more critical member than a beam. Okay. This fact can be illustrated by a bridge truss that has some of its members damaged by a trap. For example, let's imagine a truss damaged by a trap. The bending of tension members probably will not be serious, as the tensile loads will tend to strengthen those members. But the bending compression member is a serious matter, as compressive loads will tend to magnify the bending in those members. Okay. You imagine, for example, a truck crashing through a truss of the bridge. Okay. So just compare how it would affect the tension truss member and compression truss member. Okay. So compressive loads will tend to magnify the bending of compression members. Okay. Because compression would be added to another compression, so plus, no? Okay. The preceding discussion should clearly show that column imperfection causes them to bend, and the designer must consider stresses due to those moments as well as those due to axial load. Okay. So we have chapters 5 to 7 for columns. Okay. So imagine there are 3 chapters dedicated for columns. Okay. The spacing of columns, okay, in a plan establishes what is called a bay. So when we say bay, that is the column to column. No? For instance, if the columns are 20 feet on center in one direction and 25 feet in the other direction, the bay size is 20 by 25. So that is what we mean by bay. Okay. Larger bay sizes increase the user's flexibility in space planning. We want more space, we want lesser column, we want use all of the space. However, columns are necessary and critical. Okay? That's why we have to suffer the consequences of column being there, which might not be desirable. Okay? We want every space to be utilized. So column might not be visually beautiful also, but still it is necessary. That's why we have to put on the proper size, dimension, place, position of columns. As economy, a detailed study by John Roddy indicates that when shallow spread footings are used, shallow spread footings, okay, based with length to width ratios of about 1.25 to 1.75 and areas of about 1,000 square feet are the most cost efficient. Okay, take note of that. Very important rule of the thumb. Okay, what is 1,000 square foot? So let us open our calculator. Let us compute how much is 1,000 . So 1,000 divided by 3.28, so we can convert into meters. So this is about 93 square meters. Okay, 1,000 square foot is 93 square meter. So one residential lot area. So lot area of one residential unit. Nowadays, smaller and smaller residential area is being used due to what increasing prices of property of real estate. Okay. But now you can see 30 square meter lot property, 50 square meter lot property, 60, but generally 100 is about ideal, but we can usually, for example, in high density cities, places like New York, Tokyo, smaller and smaller lot area, and particularly smaller and smaller living space are being used by more than the population, majority of the population. So 93 square. So if you have 93, that is supposed to be the rule of the thumb. Okay. So let's take note of that. 1.25 to 1.75 length to width ratio. Okay. The most cost efficient. When deep foundation are used, this study shows that larger base areas are more economical. So this is just for what? Shallow spread footings. But for deep foundation, the larger, the more economical, because deep foundation is capable of and are usually designed for bigger areas actually. Okay. So residual stresses. Okay. Residual stresses and distribution are very important factors. These are of particular importance for columns with slenderness ratios varying from 40 to 120. Slenderness ratio meaning length divided by R or radius of gyration. Okay. So if you have 40 to 120 range, that includes a very large percentage of practical columns. Okay. Practical columns in practice, that is the large or majority of the application of columns between 40 to 120 slenderness ratio. A major cause of residual stress is the uneven cooling of shapes after hot rolling. So the stress is retained inside the material. Okay? For instance, in a W shape, the outer tips of the plants in the middle of the web cool quickly, of course. Okay? Because they have what? Greater interaction to the environmental air, which is cooler. So therefore, the greater the amount of interaction to the cool air, so they are quicker to cool. Okay? While the areas at the intersection of the flanks and the web cool more slowly. That is logical, and it is being what? Proved by analysis and studies, okay? Research. Okay? So always there is a presence of what? Residual stresses. So as you can see on the figure, we have ideal curve, which is a straight line and another straight line, but actually we have the W section with residual stresses. We have what? Curve in this section, okay? In this region, it is curved smoothly, okay? That is the reality, okay? This is the effect of residual stresses on columns, okay? This is again the strain, delta L over L. So stress is the force divided by area. So sections for columns. So these are the sample sections for columns. Okay. So A, single angle. B, double angle. So the double angle 1 and 2, they are placed opposite. Okay. T, regular section. C channel, a regular section. W section is a regular one. Pipe or round HSS tubing, a regular section. Square HSS, a regular. Rectangular HSS, regular. So 4 angle back section, this is built up. This is a built up section. You can use what? You can use angle, you can use plate. So by using what? 4 angle, so angular at the corners, then putting on the plates on the sides, right? Back section, also a built-up section. So with what? As you can see, 2 channel, and then put on the necessary lacing or plates, okay? Another type of back section with the C channel facing outside, right? And as you can see, this looks like a I-beam. This looks like an I-beam, okay? Another back section, but this time we have what? Plate, so a straight plate at the top, while there are several pieces on the bottom, flans, right? So it looks like an I-beam, so we have a flans and web type of section. These are built-up section. Another built-up back section using 4 angles here, angles, angle, angle. So there are 4 angles, then plate, plate, then plate, and several parts on the bottom plans. Okay. So W section with cover plates. So we have strengthened W section because a plate are attached to both of the plans, top and bottom. Okay. This is again built up section. Another W section, but this time it is built up section, built out of 3 plates, 1, 2, and 3. So they are welded on those sections. So you can use that as a compression member or as a column. Okay, you can do this. Okay, another built up section, 4 plates. Okay, so welded on corners. Okay, built up section. W channels, meaning we have a W and then attach a C channel on the upper plans and on the lower plans. Okay, so that's why it's called W and channels. Okay, another built up section looks like an I-beam, but you have to use 4 angles, 1, 2, 3, 4. So the 4 angles would function as plans and then provide the web. Okay, use a plate to function as a web. Okay, another built-up section, similar to this one, but you have to add another plate on top and bottom flange. Okay, so those are the types of columns, types of cross-sectional area column. Okay, you have to expect any one of that, and you can use any one of that. Okay, in our design, we will just take a look at the regular sections, not the built-up. So when you are going to use the built-up section, it is you can analyze it as we are analyzing the regular shape. Okay. So as you can see, we have the steel columns on beside our school. We have walkway. We have walkways with steel columns that are circular, and that is like this. HSS, pipe SSS, like this. This column, steel, pipe, round, HSS tubing column. Okay? Steel column, and they are mounted on the mounted on the reinforced concrete short column. Okay, as you can see along the side of the university. So next topic are the development of column formulas. We already talked about this from the theoretical point of view, from the manual point of view, or what we call code. So we already talked about it, and these are the textbook explanation. Okay. This is the textbook explanation of those things. Okay. So, test result curve when testing by L over R is the independent variable, and PU over A is the dependent variable. Testing several points, several specimens, and then the testing results are the dots, and then we have to represent those dots into a mathematical equation. So this is the mathematical equation. This is the curve of the mathematical equation that represents all these dots. Okay, that's why it is not precise. Okay, it is not too accurate, but the precision is already very, very good. Okay, as you can see. So really, the Euler formula is the basis of so many things with respect to compression members. Okay, so obviously the stress at which a column buckles and decreases as the column becomes longer. That is quite logical. It is easily it could easily fail if the column is longer. Okay? So for a column to buckle elastically, it will have to be long and slender. Its buckling load P can be computed with the Euler formula that follows. So as you can recall from last week, we have the curve. We tested the Euler value load P with respect to the ideal Okay, and the Euler load P is the what? The maximum. That is the maximum. Okay, and that is equal to pi squared EI over L squared. Okay, this formula usually is written in a slightly different form that involves the column slenderness ratio. So take note again, so just like what I've said, that is the definition of radius of gyration R. Okay, so divide both sides by A, so we can have what? Okay, the Euler buckling stress. So this is the buckling stress. Okay, so this is now for what? This is what we use for global buckling. No? We use for global buckling. So global or flexural and Euler formula. We have the next one, which is local buckling and torsional. So those are the failure modes as we already studied last meeting. So again, please familiarize yourself. Even better, memorize these formulas. Okay, let's go to the examples. Okay. Example 1. So we are going to determine the column's critical or buckling load. Okay, if we are given W10 by 22, okay, use as 15 feet long pin connected column. Pin connected. So take note, if you consider the connection, there is what we call K factor. Okay, and the K factor, K is equal to 1 if the column has pin connection. Recall last meeting. Okay, assume that this still has a proportional limit of 36 KSI. So A, 36 material. Okay, and letter B, repeat part A if the length is changed to 8 feet. So let us compare if really the length of the column will will influence the susceptibility of the member to fail. Okay, so let us solve problem solution. Letter A, using 15 feet long. Okay, let us get our table. W10 by 22. Do we have W10 by 22 here? W10. W10 by 22. So, can you see W10 by 22? Okay, there. W10 by 30. W10 by 12. So, you can use interpolation between this. W10, 22, you can use interpolation. Interpolate 30 and 12. Okay? Interpolate it. Okay? You have to use interpolation between this. Or you can use a better table which has W10 by 22. So let us find out W10 by 22. So W14. So W10 by 22. So we have here the W10 by 22. Okay, so we already have this W10 by 22 here. Okay, W10 by 22, and what do you mean by that? Area, depth. Okay, So what are the important things that we need to know? Area, then radius of gyration X and radius of gyration Y. Okay? So Rx, Ry. So those are important. Area, Rx, Ry. So let us take a look. That is for when we are going to use this element as a column. We need area. So this is the area. So the first column is the shape. Second one is the area, then depth. So where is the K? R? Where is the R? So the R is on the other side. So we have R, Y, R, X. Okay? So we have here. Okay? Here. RX, this is the RX. This is the RY. Okay? RX, RY. So let us... This is 22. 22. That is our 10 by 22. Okay? So Rx is 4.91. Take note, 4.91. Ry is 0.848. Okay? 4.91 and 0.848. So let us add 4.28. So that is not exact, no? 4.27. So this is 4.91. Okay? Take note. This is 4.91, but here it is 4.27. Okay? Rx is 4.27. So 10. Wait. Do we have the 1022? This is 1022. This is our 1022. So 1, 2, 3, 4, 5. The fifth one. So we are looking at the incorrect. So we have to look at the lower portion here. Here is 22. So you can see 22 here. 22. 22 pounds per cubic foot. So this is 4.27. So this is 4.27 and 1.33 for Ry. Ry is 1.33. Okay? So let's confirm 1.33 here, 1.33, and Rx is 4.27. Rx is 4.27. Correct here. Okay? And area, what is the area? Here, the area is here 10 by 22, area is 6.49. 6.49, correct. So all of these three are correct values from our AISC table. So while if you have this table, 10 by 22 is not here, you can have what? You can have this table, okay, using this area for 12 and area for 30. Let us compute. Let us verify by what? Interpolation. Let us use interpolation to be able to use this table. Okay, I will show you how to interpolate to find out the area. Okay, so and also the R. Okay, the R and R. So we have Rx and Ry here. Rx here. This is the R. Interpolate. You can interpolate this too. Okay? Interpolate. For example, let us I will only interpolate one. You can do it the others. Okay? So I will only interpolate, for example, which one? Ry? Which one do you want? Ry, Rx, or area? Which one do you want to interpolate? I will show it to you once, and then you have to do the others. Okay? Which one do you like? Type your answer on the what? On the chat. So there are no one listening. There are no answer. Okay, anyway, I will do it myself. If there are no answers, so I will just select RY. So I will just select RY. Okay, RY. I will interpolate and show you. My calculator here. So RY. Where is the RY? Here. 1.37 and 0.785. Okay, so remember that. So we have what?